Hello viewers. In this session, I would like to discuss on the plastic analysis of the continuous beam. So, for the example has taken this beam. The beam has two span and three concentrated loads. Each concentrated load is acting at 2 meter span on the 2 meter distance on the span of AB, and it is 2 meter from the support B. And one end is fixed, other two are simply supported. So particularly this plastic analysis of the continuous beam is to be referred by considering kinematic method of analysis. So whenever we do got the different loading conditions, we have to remember the mechanism of the plastic analysis. So mechanism in the sense, so whenever the different kinds of the loads are acting on this different span, under the concentrated load, plastic hinge is to be expected, and when at the fixed support we do expect the plastic hinge, and on the continuous support we do expect the plastic hinge, and at the simply supported on the left side we do not expect any plastic hinges. So that means in the span of AB we will be having two concentrated loads having two mechanisms, and in the span of BC we have one concentrated load and one mechanism. While starting this plastic analysis, we have to draw the diagram of each mechanism, and later we need to consider the kinematic method of analysis, which is nothing but equating external work done to internal work done. So now I would like to draw this mechanism 1 for the given beam of span AB. So this will be, so first I will consider for 100 kilonewton and later I will consider for 150 kilonewton. So under 100 kilonewton, if I take this reference line, this would be the deflection we can expect under the 100 kilonewton load, and here if I take, it is 150 kilonewton load. This is for case 1 I can say, or mechanism 1, so which has 100 kilonewton. So here at this support I do get plastic movement. So here we need to observe that the plastic movement is given 1.5 times for the span AB. So it is 1.5 times for the span AB, right? And here it is MP only, because on the other support it is only MP. So at this support I will get 1.5 MP. So now when this 100 kilonewton load is acting on the span AB at a distance 2 meter from the support A, I do expect some rotations here, which is theta 1, and again because of this 100 kilonewton load there is a rotation on the support B, which is theta 2, and deflection is delta 1, and deflection at the 150 kilonewton load is delta 2 which is acting 2 meter on the span AB. And here if I take at this point, this theta 2 will be reflecting on the other side, this angle, and this theta 1 is this one. So this angle must be equal, right? These two angles must be equal. So this is for case 1. So for this case 1, now I would like to consider, this is support A and this is support B. So now what I will do, I will start writing for internal work done. So to start the internal work done, I would like to take the relation between this delta 1, theta 2, right? So what I do, I will write this delta 1 equal to, whenever I do start for plastic analysis for the internal work done, I must start with a deflection under the considered load. So here in the case 1, 100 kilonewton load is considered. So delta 1 can be written as 2 theta 1 or this 4 theta 2. So this delta 1 can be written as, if you consider this triangle, this base dimension multiplied with the adjacent side, and for this delta 1, if I consider this triangle, I could write 4. This is from distance from here to here, it is 4 meter to theta 2, that is 4 theta 2. So theta 1 can be written as 4 by 2 theta 2, right? Theta 1 is 2 theta 2. So theta 2 can be written as 0.5 theta 1, reverse of this one, 1 by 2, right? This is what. Now what I got? I have got the relation between theta 1 to theta 2. So theta 1 is 2 times of the theta 2 under the load of 100 kN load. So now I will write internal work done. Internal work done. So if I want to write the internal work done, how I can write? See, now I need to go from support A and hinge at concentrated load and support B. So in this part I am considering the case 1 for 100 kN load, and later I do consider for 150 kN load. So now for case 1 it is considered for 100 kN load. So this is the plastic hinge is expected 1.5 MP theta 1 plus, here I got 1.5 MP theta 1 plus theta 2, and here I got only MP because on the other side I got only MP plus MP theta 2. So this is what the internal work done. So now I have got the relation, right? I have got the relation from theta 1 and theta 2. Either I can substitute theta 1 as theta 2 in this equation, or I can substitute theta 2 as 0.5 theta 1 in this equation. Any one of the relation can be substituted and obtain the value of this internal work done in terms of theta 1 or theta 2. So now what I do, I will consider I will from theta 2 as 0.5 theta 1. So 1.5 MP theta 1, 1.5 MP. So if I multiply here, it is theta 1. Now it is theta 2. Theta 2 can be substituted as 0.5 theta 1. I am considering this theta 2. Either you can consider theta 1 also. So 1.5 MP. This is multiplying this 1.5 MP to theta 2 can be written as 0.5 theta 1 plus this MP 0.5 theta 1. So now we got all the values in theta 1, just we need to sum up this 1.5 and 1.5 is 3, 4.5 and 4.25. So it is multiplied with this one, this is 4.25 MP theta 1. It is 1.5, 1.5 is 3, and here it is 1.5 times 0.5, it is 0.75 plus 0.5, 1.25. That is 3 plus 1.25 is 4.25 MP theta 1. Now it is internal work done for case 1. Similarly, I need to write it for external work done. External work done. For this external work done, what I can do? Now in this case, I want to take the relation between this delta 1 and delta 2. As I have taken internal work done for theta 1 and theta 2, I need to take for the external work done is delta 1, delta 2, because internal work done is measured for its rotations and external work done is measured for its deflections under the each load. In that case, I am considering this delta 1 and delta 2 for external work done. So what I do consider this triangle, writing delta 2 by delta 1, considering these similar triangles. So this delta 2 is one triangle and delta 1 that conforming to another triangle. So delta 2 can be written as 2 theta 2, right? So theta 2 will be cancelled here, so 2 theta 2, and delta 1 can be written as 2 plus 2, 4 theta 2, right? So it is delta 2 can be written as 0.5 delta 1. Delta 2 can be written as 0.5 delta 1, or delta 1 can be written as 2 delta 2. Delta 1 can be written as 2 delta 2. In both cases we can solve it for. So now our aim is to get the external work done. The external work done is obtained by considering load under deflection, right? So for that, what I do, I will write 100. For this 100 kilonewton load, I got a deflection delta 1, plus under this 150 kilonewton load, I got deflection delta 2. So apart from these two loads, I do not have any other load in the span of AB, because I am doing it for case 1 for the span of AB. So 100 times delta 1 and 150 times delta 2. Now I can substitute delta 1 as 2 delta 2 or delta 2 as 0.5 delta 1. So what I do, I will consider this delta 2, 100 delta 1 plus 150 times delta 2 as 0.5 delta 1, right? So if you solve for this, it will be 175 times delta 100, and this is 75 times delta 1. So now in this delta 1, if you consider this delta 1, what is delta 1? Delta 1 is 2 theta 1 or 4 theta 2. So in either of these two, which one needs to be considered? So, on the basis of internal work done. So in this internal work done, I have observed the value in terms of theta 1. So I must substitute in terms of theta 2 to equate this internal and external work done. So if I take this in terms of theta 2 for internal work done, I must take this delta 1 relation in terms of 4 theta 2 only, because I need to relation between internal work done and external work done. So what I do, delta 1 equal to 2 theta 1. This value I am going to substitute. So it is 350 theta 1. Now internal work done equal to external work done. Internal work done equal to external work done. So internal work done is this one, 4.25 EMP theta 1, and external work done is 350 theta 1. So this theta 1 will get cancelled. So EMP equal to 350 by 4.25, which is 82.35 kilonewton meter, right? So which is 350 divided by 4.25 is 82.35 kilonewton. So this is for case 1. So similarly, I need to consider for the second mechanism for the same span AB. So now whatever I have done, it is for the under load of 100 kilonewton load, and I need to do it for case 2 mechanism for 150 kilonewton load. Now I am doing it for case 2. Case 2 is for under load of 150 kilonewton for the span AB. So for here, under the 150 kilonewton load, I am considering deflection delta 1, and under 100 kilonewton load, I am considering deflection delta 2. And because of this, I am considering rotation theta 1 at support A and rotation theta 2 at support B. And this delta 1 is 2 meter from support B, and this 2 meter from here and it is 2 meter from here, right? So now at this point I got 1.5 mp because the support A has got 1.5 mp for the span AB, and here also it is 1.5 mp. Here it is mp only because on the other span it is mp. Now for theta 2 it is the opposite sides, it is theta 1 on the opposite side. So now I need to consider internal work done as well as external work done. Similar procedure is to be followed. So now what I do, I will consider this relation again, this delta 1 relation for the span of AB. To consider that, what I can write, delta 1 can be written as 4 theta 1 or 2 theta 2. 2 theta 2. So this delta 1 can be written as 4 theta 1 or 2 theta 2, referring the triangle, this triangle and this triangle. So this is the height and this is the adjacent hypotenuse and this is the adjacent side. So now theta 1 can be written as 2 by 4 theta 2. Theta 1 is 0.5 theta 2 or theta 2 is 2 theta 1. Okay, so now I am going to write internal work done. Internal work done. For this internal work done, what I can write, I need to refer the plastic moment at point A, plastic moment under the load, plastic moment at the continuous support. So 1.5 mp, 1.5 mp theta 1 plus 1.5 mp theta 1 plus theta 2 plus mp theta 2. Theta 2. Again, either theta 1 can be substituted as 0.5 theta 2 or theta 2 can be substituted as 2 theta 1. So here what I do, I will substitute theta 2 as 2 theta 1. 1.5 mp theta 1, 1.5 mp theta 1 plus 1.5, I am just multiplying this, mp theta 2 can be written as 2 theta 1 plus mp 2 theta 1. So it is 1.5, 1.5, 3, and it is 1.5 times 2, it is 3, and it is 2. So total 3 plus 3, 6 plus 2, 8 mp theta 1. 8 mp theta 1. Now external work done. External work done. So external work done is deflection under the load. So now for 100 kilonewton load, for 100 kilonewton load, I got deflection delta 2, and 150 kilonewton load I got deflection delta 1. So 100 kilonewton delta 2 plus 150 times 150 delta 1. To substitute this delta 1 and delta 2, I need to take the reference of the delta 1 in terms of delta 2 or delta 2 in terms of delta 1 by referring this similar triangle. Similar case, what I have done for case 1, I have referred this triangle. For case 2, I am referring this triangle. So similar triangle, delta 2 by delta 1, this delta 2 is 2 theta 1 and delta 1 is 4 theta 1. So delta 2 can be written as 0.5 delta 1 or delta 1 can be written as 2 delta 2. Just I do substitute either delta 2 or delta 1 in this external work done. So what I do, I will substitute this delta 2 as 0.5 delta 1, 100 times 0.5 delta 1 plus 150 delta 1. So it is 75, sorry, it is 50 plus 100, 200 delta 1. Now this delta 1 is to be substituted in terms of theta 1 because that is one I can equate this internal work done as and external work done. So delta 1 can be written as 4 theta 1 or 2 theta 2. So here I do consider 4 theta 1 because I have got in terms of theta 1 in internal work done. So 4 theta 1 is to be substituted. So 200 into 4 theta 1, it is 800 theta 1. Okay, so now equating internal work done equal to external work done. So if I equate this, internal work done is 8 mp theta 1, external work done is 800 theta 1. So this will get cancelled. Thus mp is 800 by 8, which is 100 kilonewton meter. So this is for case 2 or second mechanism for the span A and B under the load of 150 kilonewton. Now mechanism 3 or case 3 for span of BC. For the span BC, the case 3 is to be done under the load of 80 kilonewton load. So under this 80 kilonewton load, if it is acting on span BC, the rotations are expected to have theta 1 on the support B, theta 2 on the support C, and the opposite angles are theta 1 and theta 2 at the point under the load, and plastic moment is expected to have at point B or support B, which is continuous and under the concentrated load. And at this point we do not get any movement because it is simply supported, and at the end if we got another support, continuous beam over here, we will get the movement over here. But since it is the end support which is simply supported, then we do not get any movement at this point. So in the mechanism 3 or case 3 under the load of 80 kilonewton load, we do expect the plastic movement at support B and under the concentrated load only. So now for this, if I want to take this plastic analysis, the delta 1 can be written as 2 theta 1 or 3 theta 2. Delta 1 can be written as 2 theta 1 or 3 theta 2. So theta 1 can be written as 3 by 2 theta 2, 1.5 theta 2, or theta 2 can be written as, so it is 1 by, which is 2 by 3, which is 2 by 3. So it is reverse, or 1.1 by 1.5, it is 0.67 theta 1, right? So now internal work done. If I want to write internal work done, what I could write? So it is mp, this mp theta 1 plus mp theta 1 plus theta 2, and we do not have any MPs here, and means movement is not there. So it is at this point. So now theta 1 can be substituted as 1.5 theta 2, or theta 2 can be substituted as 0.67 theta 1. So what I do, I will substitute this theta 2 itself. So mp theta 1 plus mp multiplying this mp theta 1 plus mp theta 2 is mp theta 2 can be written as 0.67 theta 1. So 1 mp theta 1 and another mp theta 1 is 2 mp theta 1 and 0.67, which is 2.67 mp theta 1. Now external work done. So external work done is deflection under the load. So deflection under load is 80 kilonewton, deflection is delta 1. So 80 times delta 1 only, because other than this 80 kilonewton load, we do not have any other loads on the span BC. So delta 1 can be substituted as 2 theta 1 because internal work done is in terms of theta 1. So 80 times 2 theta 1, which is 160 theta 1. So internal work done equal to external work done. So internal work done is 2.67 MP theta 1, 160 theta 1. So this will get cancelled, though MP is 160 divided by 2.67. It is 59.92. 59.92, 60 kilonewton meter can be written. So MP for the span BC is 60 kilonewton meter. So now if we take the summary, case 1 got MP as 82.35 kilonewton meter. Okay, and for case 2 or mechanism 2, MP we got it as 100 kilonewton meter. And for case 3 we got MP as 60 kilonewton meter. So here the plastic collapse moment for the continuous beam is 100 kilonewton load. So the maximum capacity of the beam is 100 kilonewton load for the span AB. Okay, so now plastic movement capacity for span AB is 100 kilonewton, but in the question we got 1.5 MP, so it is 1.5 times MP is 100, so it is 150 kilonewton meter. So similarly for span BC it is 80 kilonewton. Under the 80 kilonewton load it is 60. So it is just we can have for 60 kilonewton meter. So plastic moment capacity for the span for the continuous beam is 100 kilonewton load. For span AB it is 150, and for span BC it is 60 kilonewton. So this is what the plastic analysis of continuous beam by referring the kinematic method of analysis. Thank you.